this lecture we continue with a discussion on logic synthesis. Now, if you recall, in our last lecture we had looked at several schemes for carrying out logic synthesis for both two-level and multi-level realizations. We talked about the essential idea behind methods like Socrates or MIS. Now, in this lecture today we shall be looking at an alternate method using which you can also perform logic synthesis. In fact, this method is more general and powerful, not necessarily used or applicable to logic synthesis alone. It has much wider range of applicability. Before going into the method, we first let us look at or talk about some alternate representations of Boolean functions. Well, when we are talking about representing a Boolean function, there are broadly two ways of doing so, canonical and non-canonical. Canonical means these representations are unique. Given a particular Boolean function f, you can have a unique truth table, a unique Carnot map, or a unique set of minterms. Okay? That is why we call this as the canonical representation. But however, there are again several representations of a function f where you can have several different ways of doing so. For example, sum of products. Given a set of minterms, you can combine some of them into bigger cubes to perform minimization, and after minimization it is possible to have several alternate sum of products formed for the same function. Similarly for product of sums. And again, a given function f can be factored in a number of different ways. You can have several different factored forms. Now, here we are interested in the representation called binary decision diagram, which is called BDD in short. Now, you will see BDD is also not a canonical representation in the sense that the BDD, the nature and the look of this diagram can vary depending on certain parameters. So, here we will be looking at the binary decision diagrams. BDD or the binary decision diagram was initially proposed by Akers as early as in 1978. Now, it was primarily used for representing Boolean functions, as we shall see shortly. Now, the original definition of BDD were subsequently refined and several variations were suggested. Well, one of them is called ordered binary decision diagram, where some kind of ordering is enforced. We shall be seeing that. And after we get this ordered binary decision diagram, there are some operators which are defined using which we can carry out some minimization or reduction on that diagram. This is called reduced ordered BDD or ROBDD. So, actually for practical purposes we will be using ROBDD for the representation and manipulation. So, in order to get this ROBDD starting from a BDD, so a set of reduction rules and operators have been defined which can be applied successively on a given binary decision diagram in order to obtain a ROBDD. Now, the way a BDD is constructed, you see, it is essentially based on the so called Shannon expansion of a given function. So, first let us try to understand what this Shannon expansion is, and then we shall be explaining through examples how a binary decision diagram can be constructed. Okay. So, Shannon expansion for a function, well, the definition can be given like this. Suppose we have an n variable Boolean function f. F is a function of x1, x2 through xn, where xi is an intermediate value. Now, we define positive and negative cofactors as follows. A positive cofactor f suffix I 1 is the same function where the input variable xi replaced by a 1. Okay. So, when the ith input is replaced by a constant 1, then the resulting function is called the positive cofactor and is denoted like this. Similarly, if the ith variable is replaced by a constant 0, then we call it negative cofactor, represented like this, fi 0. Now, according to Shannon's expansion theorem, a function f, when expanded with respect to an input variable xi, can be written like this: f equal to xi prime negative cofactor with respect to I, or xi positive cofactor with respect to I. So, this is the expression which we will be making use of when we will be constructing binary division diagram. So, essentially it means that I take out xi prime and I can replace the ith variable by 0. I take out xi, I replace the ith variable by 1. Now, it can be proved that this indeed gives the original function. And if you are more interested in the product of sum representation, then the alternate form is this: xi or negative cofactor, xi prime or positive cofactor. So, in this way you can represent or expand a Boolean function with respect to an input variable. So, let us take a simple example to illustrate this. Suppose I have a function of 4 variables, say a, b, c, d. Say the function is a, b, c, or b prime, c prime, d, or a prime, b, d prime. Okay. Suppose we want to expand this function with respect to input variable a. Well, first let us try to see how we do this normally. Normally, this function can be written like this. Well, ABC is already there. The second term is independent of A, so we can write like this: A prime, B prime, C prime, D, or A, B prime, C prime, D. Actually, we are introducing A here, A prime and A. Similarly, this contains A, no problem. So, by doing this, what we have achieved is that each of the product term contains some term of A, either complemented or uncomplemented. So, after that we can simply take A prime common, B prime, C prime, D, or B D prime. You can take A common, B C, or B prime, C prime, D. So, this is the so called Shannon's expansion with respect to A. Now, you can even check that with respect to the formula we had just mentioned, this one, if we apply that same rule, what happens? See, the same thing if you do with respect to the negative and positive cofactors, you see the formula once more. It is xi prime multiplied by the negative cofactor. So, what we can write as per that formula, A prime into negative cofactor means the function f where A is replaced by 0, okay, or A, the function f where A is replaced by 1. Now, you can find out the values of this negative and positive cofactors from this original expression. Let us see. A prime, if you replace A by 0, just put A equal to 0 here. This first term goes away, you have B prime, C prime, D, and this becomes only B D prime. Similarly, for the second one, replace A by 1, this term goes away, this becomes B C or this. So, you see, actually it is the same thing, whether you do it using logical manipulation or you directly apply Shannon's formula, it is actually giving you the same function. So, you understand one thing, starting from the given function, you can do or carry out the expansion with respect to an input variable A or B or C or D. Depending on which variable you are using for the expansion, well, you will be getting different forms of the function. Now here another thing, let us also understand intuitively that why we are doing or carrying out this kind of an expansion when we are saying that our objective is to synthesize. See, when we expand a function with respect to A, you can think it like this, that we have a multiplexer. We have a multiplexer which we control with the input variable A. Now, if the input variable A is 0, then some input is selected. If it is 1, some other input is selected. Now, somehow what we will be doing, we will be feeding the first input with a circuit realizing the first subfunction. We will be feeding the second input by a circuit realizing the second subfunction. Then our purpose is served. So, in this way we can have a very regular synthesis procedure where this circuit can be implemented using a network of multiplexers. Similarly, these functions which are there, which are independent of A, they may be expanded by some other variable, say B or C, and you can repeat this procedure. We will be having a tree of multiplexers. Okay? Fine. But before going into that, first let us see what is a binary decision diagram now and how do we construct it. Okay. Fine. So actually binary decision diagram follows very closely from the Shannon expansion as we have just mentioned. Suppose we have a given function f like this, and through Shannon's expansion we can follow the same procedure. We can write the function like this: a prime, this will be the term with it, and a, this will be the term with it. This you can very easily say, because the middle term you can write a prime bc or abc. So a prime bc will come with this and abc will come with this, and c or bc can be minimized, it is only c. So this is the ultimate form. Now in a binary decision diagram, the way we show this, that initially the function f was there, we are expanding the function with respect to the input variable a. Now this we show like this by a diagram where a is a node of the diagram, node of the figure. This is actually a tree. The root is the function f, it feeds the first node a, and you see that a has two arcs pointing downward. One is dotted, other is solid. Well, you can also show them by different colors if you want. It is just a matter of convention. Say suppose we show the dotted one by red and the other one by blue. This means the dotted one means that if the value of this variable a is false, means 0, then you will be following this path. If the value of a is true, then you will be following this path. So according to this formula, the left path, this block will correspond to b prime, c prime or bc, and this block will correspond to simply c. This you can repeat. Similarly, this sub block you can expand with respect to b and you will be getting a diagram again. So we will take an example. Okay, this same example we can work out, no problem. We had this a, we had the dotted arrow and the solid arrow. If you recall, the left side was b prime, c prime or bc. Okay, b prime, c prime or bc. Suppose we choose to expand this with respect to b, so we will be getting a node b out here. So if b is prime, c prime comes with it. Okay, so this side will get c prime and this side will get only c. So just remember, this side is c prime, this side is c. In the next step, here we will be expanding with respect to c. Now we have only c prime here. Okay, so this can be written as c prime into 1 or c into 0. So, we will be getting final final terminal nodes of a 1 and a solid one as 0. Similarly, the other side is only 0. So, if you expand with C, it will be 0 and here similarly this side was only C. Okay. So, C can be written as both side So, this is the complete binary decision diagram we have constructed. So, you see that you are given a function f. From the function f, we go on expanding using Shannon's theorem the function successively with respect to some input variable. Say here we have taken first a, then b, then c. So, ultimately as we go down the tree, finally we will be landing up into nodes which correspond to constant zeros and ones. That is the end of the story. So, the tree would be constructed till we reach the final level where the leaf nodes are all the constants zeros and ones. Now I earlier mentioned that this binary decision diagram is not a canonical representation, means it is not unique, because the same function, if you have tried to draw the BDD by using a different variable ordering, like you have taken B first, then A, then C, then your diagram would have been different, right. So, the point to note is that the binary decision diagram BDD depends on variable ordering. So, if for a particular case you fix up the ordering, like I will take A first, then B, then C. If the ordering is fixed, then you say you have got something called a ordered binary decision diagram, OBDD. So, actually this is a case of OBDD provided you have fixed up the ordering ABC. Okay. Now, once you have obtained an OBDD, there are several steps you can follow to minimize or reduce the size of the tree. So, first let us look at the reduction rules, then we will take an example to illustrate. The first reduction rule is this. It says that if in the graph you have two nodes like this, where these are the negative edges or the dotted lines, these are the positive edges. Then if from a node both the negative and the positive edges are leading to the same node in the second level, then you can omit this x, because it does not depend on x. Whatever is the value of x, you will come to here. So, after reduction you can omit x and you can have only this node y. Fine. So, this is one reduction rule. If from a node both the arcs lead to the same successor, you can omit that node. And the second set of reduction rules say that if you have a scenario like this, where there are two different nodes both labeled with x, whose successors are same, say y and z, both are y and z, then see the sources may be different. This may be coming from one place, this may be coming from some other place. these are two subgraphs in your BDD. Now, here what you do, you combine these two nodes into one. The successor links are merged together. So, instead of having two different arcs to y, you have a single arc to y, similarly single arc to z. And these two sources from where arcs are coming to here and here, you put them both into the same node. Okay? Yes?
So, the two subnodes have to be at the same level?
Not necessarily. So, actually when you are carrying out reduction, you will see that the two subnodes need not necessarily be at the same level, but if they are labeled with the same x, they have to be at the same level initially, because the order in which you are expanding A, B, C, so all A's are at the same level, B's are at the same level, C's are at the same level. Okay. Well, and the second set of rule is identical, the only difference is that the arcs which are coming in, they are negative arcs, but the rest are the same. These two are negative links, these two are positive links. So, you can merge these two and this is the positive link. So, if you have nodes like this where the successors are the same, you can merge them together provided the sources are also of the same type, but if one was dotted, other was solid, you could not have combined. Okay. And one last way of reduction, that is that is of course trivial. See, at the lowest level, I am taking a small example, at the lowest level you have only constants 1 and 0, say 1 0 0 1. Suppose you had this kind of a thing where there was an arc coming from top level to here, then to here, then to here, then to here, say these are the 4 arcs coming. Now, what you do, what I am saying, that instead of having so many terminal nodes labeled with either 0 or 1, you have a single 0 and a single 1, merge them together, and there are 4 different sources, okay, one here, one here, one here and one here. Now, this source was coming to 1, so take it to 1. This was coming to 0, so take it to 0. This was coming to 0, take it to 0, and this was to 1, take it to 1. So, this way you complete the edges, but these 1s and 0s you merge together. So, once you apply all these steps repeatedly, you get a diagram which is smaller in size, it is reduced, and this is what is called reduced ordered binary decision diagram, ROBDD. Now, let us try to illustrate ROBDD with that same example I had shown you earlier. So, let me take that same example. This was the original BDD which I had drawn. This was drawn with respect to a specific variable ordering, first A, then B, then C. So, starting from this diagram, let us now try to systematically see that what are the rules we can apply and we can minimize. One thing we can see, these two nodes, they are identical, you see, these nodes and their child, they are identical. Okay. So, what we do, I am drawing the modified diagram. So, from this diagram, I am just showing you the modified one. So, initially you had A, then you had B, now on the left side you had one out here, 0 out here, 0 out here and 1 out here. But on the right side you just see that on the right side you had something like this. You had under B C01, C01, the same thing. So what we do, instead of having two copies of this, we merge them into a single copy. So we have C 01, and from B you see there was one dotted arc coming and one solid arc coming. So we add both a dotted arc and also a solid arc. This diagram captures the same information, that from B, if you have a dotted arc, you come here, if you have a solid arc, also come here. Because since the subtrees are identical, we can keep one copy and you can just point all the arcs to there. Now after doing this, now you find that you get a situation where both the complementary and uncomplementary arcs are pointing to the same node. So you can omit B. So in the next step, you get a diagram left side still remains same, but this side from this B is no longer there. Okay, B you have omitted. From A you straight away come to C. From C you have 0 and 1. So this one node you have omitted. Okay. Now again you observe that in this diagram there are some subgraphs which are identical, this one and this one. C with the dotted arc pointing to 0 and the solid arc pointing to 1, both are the same. So again following the same rule, we would be using only one copy of this and we would be pointing the two edges to there. So after this modification, the graph will look like this. This part remains same, but here you have only one C 0 on the left side, 1 on the right side. You have arcs from A coming here like this, also arc coming from B. So there will also be arc coming like this. So you see, as we carry out the transformation, the tree becomes a graph. It is no longer a tree now. Okay, this becomes a graph. So you inspect that if you can do any other transformation, you see that you cannot do anything else. As per those rules, only other than merging the zeros and ones, you cannot do anything else. So as the final step, you merge these zeros and ones into a single 0 node and a single 1 node. So you have one C out here, another C out here. So at the lowest level you have one 0 node and one 1 node. From C dotted to 1, solid to 0, and from here dotted to 0, solid to 1. This is your final ROBDD. Now here the point to note is that the BDD representation is not canonical, I told you, but OBDD is. Once you have fixed up the ordering, the BDD will look the same. And if you apply the reduction rules, the ROBDD will also be canonical against a given variable ordering. So if the variable ordering you have fixed up, then this ROBDD is also a canonical representation. Say the same function, if we have two different ways of representing it, so means we have two different sum of products form, but if you construct the ROBDD with respect to the same variable ordering, you will finally land up into the same diagram. Okay, fine.
Even the OBDD will be the same.
OBDD will be the same, because you try to understand what is OBDD. I am expanding with respect to variables. If it is true this side, if it is false, go to the other side. And another thing, if you look at this diagram again, you will also observe another thing, that in this diagram you see this is the root, and finally you are landing up into the nodes zeros and ones. See, if you finally land up into 1, it means that for this particular input combination the function is true, 0 means it is false. Now you try to find out what are the different paths from the root up to 1. Now in this case you will see that the paths are several. There is one path like this, there is another path like this, there is another path like this. I think that is all, no? These 3 paths are there. Okay. So from this you can straight away write down the function also. For this it will be A, C, both are solid arcs. The first min term will be AC, means first product term will be AC, the second one will be, this is dotted, A bar, solid B, C, A bar, B, C, this one A bar, B bar, C bar. So just by scanning the BDD or the ROBDD, you can also find out that under what input combinations you will be getting the function as true. Okay. And you can do similarly for the false, under what combinations it is 0. Okay. Now some advantages of BDD. First thing is that, well, this, yes.
So we are converting, when reducing BDD, we are converting a tree to a graph.
While reducing BDD, we are converting a tree to a graph, yes.
So isn't that a sort of disadvantage? There were some algorithms which work efficiently on a tree.
Yes, very much true. I understand your question. You are saying that a tree was the data structure which you had initially for the OBDD, but after transforming it into OBDD, we have destroyed the tree property. Now it is a graph, and algorithms which apply to graph are more complex. True, but you understand, for an n variable function, the size of the OBDD is of the order of 2 to the power n. So for a big circuit, n is large, the amount of memory you will be requiring to store the OBDD will be huge. But after reduction, memory can be manageable. That is why we go for ROBDD, nothing else. That is a compact way of representing the function, that is all.
Is there any gain in terms of hardware?
See, hardware, it depends. If you are, see, whether you are using ROBDD or OBDD, it really does not matter the way you process it. I will give an example shortly, that ultimately you will be landing up into the same hardware. Because in ROBDD also we are capturing the same information. We are, say that wherever there are similar things, we are trying to combine them together. That is all, okay. Fine. Now some advantages or benefits of ROBDD, let us see. First thing is that checking for tautology. If the function is a true function, f equal to 1, then the BDD will be a constant one, no ABC, just a single node 1. It is trivial, obviously. The second thing is complementation. Suppose I have a function f, I have a BDD for it. I want to construct the BDD for a function f prime. So what I do, I simply exchange the 2 terminal nodes, nothing else, everything else remains same. I make the 0 as a 1, 1 as 0, that is all. And equivalence check is also easy, provided you have the same variable ordering. Because as I told you, both OBDD and ROBDD are unique under the same ordering. So if you can enforce that you are using the same variable ordering, then checking whether 2 functions are equivalent or not, that also becomes easy. Fine. And a point to note is that, see, from BDD we are drawing OBDD, but we really do not know which ordering of the variable would be better for us. the size of the BDD after reduction, that means we are actually talking of ROBDD. The size of the final ROBDD can vary drastically depending on the order of the variables. So, there is no deterministic algorithm which will tell you that well this variable ordering is the best, but of course there are some heuristics which people use, like you try to use a variable for breaking up or splitting a function which approximately divides the number of true min terms into half and half false and half true. So, you try to use a variable like that. Well, you can count the number of literals in the two sub functions and find out whether they are approximately equal. So, if you can split it up into half at each stage, that will be most probably the most efficient way of splitting. Those are heuristics, but it is not necessarily true that if you do that every time you will be getting the best, but for most of the time you will be getting good results. And the worst case, as I told you, that the number of nodes can be exponential, and even in extreme cases after reduction also you cannot reduce much, it will still remain exponential. So, the size complexity of a BDD in the worst case is 2 to the power n, but for most functions after reduction we get a drastic reduction. But you can always have a function like the exclusive OR function, again that extreme example I am taking, that BDD it is very difficult to reduce, you will not be able to reduce. Okay. Fine. So, this concept of reduced order binary decision diagram, this has been used by many researchers primarily for the representation of Boolean function, for simulation, for verification, even for synthesis. Now, in this context we will show you one method which was used where BDD was applied for synthesis. But first you observe, well, BDD is canonical for a given variable ordering, I have already mentioned. But one thing you just observe, the BDD it somehow implicitly uses factored representation. The transformations that we are carrying out, that is implicitly doing that. Like whenever we are eliminating a node like x, when it was leading to the same node at the next level. So, in terms of the Boolean expression, the left side what it was indicating, that if x is false come here, if x is true come here. Suppose the sub function that is under this y, let us call it h. So, this function is x prime h or x h, this one. Now, after reduction we are calling it simply h. So, it is just a factored form, you just take h common, x prime or x is 1, you minimize it. Similarly, when you have something like this where both a and b are coming in here, you put them in the same place. Now, again this sub function is h, this sub function is also h. So, the left hand side it was ah or bh, and when you do this as if we are combining them together, a or b h. So, these reduction rules that we are carrying out, that while constructing ROBDD, this implicitly captures the factored information and implicitly does some minimization for us. Okay? This is the idea.
Sir,
Yeah.
and B side had we had a dotted line, then also could have combined them by this rule.
If B had a dotted line,
So there, because it is AH and B prime H.
it would have been B prime. Yeah, yeah. You could have. If this was a dotted line, then this was a dotted line, then this would be A H or B prime H. Yes, you could have. Yes, true. Fine. Now let us look at how BDD can be used for synthesis. So I told you before that very naturally the way you are expanding a function while constructing BDD, there is some kind of a multiplexer realization which immediately comes to your mind. Suppose you have a scenario like this, a scenario where we have a node labeled x out here. If x is false, you come to a subtree out here. If it is true, you come to a subtree out here, and this subtree realizes, well, this is f, let us call it something else, h, realizes h, this realizes g. Then this you can map into a partial hardware realization where this node x is modeled by a multiplexer. This multiplexer is having a control line as x. The output of the multiplexer is the function, and the inputs, one of them is being fed by a subcircuit realizing h, other by g. Okay. So, as a very simple example, let us take a very simple example. Say I have a function a prime b prime or a b. So, if I very quickly draw the BDD for this function, for the function f, we start with a, one and 0, 0 and 1. Unfortunately, for this function you cannot do any further reduction. This is already in the reduced form. Now, this if you want to map into hardware, you will be having a multiplexer whose control input is a, I am talking about this level, okay, breaking up with respect to a. The output is f, the two inputs to the multiplexer, the left input and the right input. If it is false, I am coming to this. So, I must feed this sub function which I was calling h. Now, well, in this example, this sub function is nothing but b prime. If b is true 1, if b is false, if b is false 1, if b is true 0, b prime. So, here you will have to feed b prime and here you will have to feed b. This is the idea, basic concept. And in general, if you have a scenario like this, where you have a general BDD, I am showing it in abstract form, where you have a portion of the BDD, this we are calling as H. This H is not a single node, rather this H is a portion of a BDD, and from H you have a point which is feeding to a subfunction f. Well, let us call it h again, this I have used the same notation h. This h is already there, let us call it say m. Okay. So, then you can have a realization where there is a multiplexer with m and g below it, but the control input is fed not by a single variable, but by another circuit which is realizing h. If h is true, I will follow the right path. If h is false, I will follow the left path. See, a subfunction with two subfunction under this means that this is the false path and this is the true path. Okay. So, let us take an example to illustrate this. Suppose I have a function like, okay, I am just working this out. I will show this diagram after this. Suppose I have a function, well, I am drawing the BDD straight away. Suppose I have a reduced order BDD which looks like this. It is a 4 variable function. This. Suppose I have a BDD for this which realizes a function f. Now, somehow I will have to cut this graph so that the false path will point us to the left and the true path would point us to the right. See, there are different ways of doing it. What we can do is that we can cut this, say, at this level. So, after A and B we can cut this at this level, and what you can have, we can have a realization like this. This is a multiplexer whose output is F, and the control input which is feeding, I am showing it in abstract term. This is a circuit which implements the two inputs out here. This is the 0 input and 1 input. This implements another circuit corresponding to the BDD, and this implements another one which corresponds to say, it is just a matter of convention. The left one I am treating as 0, the right one I am treating as 1. See, with respect to this, the only thing I want is that under some condition I will go left, under some condition I will go right. Well, here you really cannot tell that this is false or this is true, but you can just tell that this is left and this is right. So, just based on that convention I am calling the left one as 0, right one as 1, and if it is left, then you have to come here C01, and if it is right, you have to come here D01, right. So, this is the requirement of your function, and this one you see that this is simply C, this is simply D, and this, if, well, I am showing this diagram now. This is drawn in that compact form. The left input is simply C, right input is simply D, but what is this function? You can again follow that same rule, you trace all parts of the true minterm A B bar. So, this actually is the function A B bar. So, you see that this way of synthesizing a function is in a sense hybrid. That means, you are not getting a purely a gate level realization. There are some multiplexers, there are some small functions you get which you will have to realize using gates. Like here your final implementation will be, you will be getting the multiplexer, one multiplexer is needed, and here you need some function for AB bar. Well, if you are using NOT and AND gates, so you will have to generate B bar, use an AND gate and feed it. Here you get C, here you get D. So, there are many synthesis tools which actually use a process similar to this. So, it does not always synthesize a combination logic using gates only. You will find that there are multiplexers and other block logic, multiplexers, decoders are also sometimes used for synthesizing a function. Now, the advantage of using multiplexer is that if your way of representation or the way you are representing is through ROBDD, then this multiplexer based realization comes very naturally, right. So, yeah, you can cut this at any level. See, you can cut this at any level provided you can identify which is left, which is right. Say you can cut at the level of A also, then you know that this part is left, this part is your left, and this whole part is your right. Okay. So, you can cut at any level, but you will have to remember this mapping.
The way we cut our final hardware thing will depend on this.
Depend on this. So, just you will have to do some kind of a balancing. That means again the best point to cut will be the place where there is minimum overlap between the two. If you cut at A, you you will see that this C node is common to both. So, you will have to cut in one place where there is minimum overlap between the two, and approximately they are of equal sizes. There are some heuristics which are used to that. So, to summarize finally, these binary decision diagrams, this was traditionally used to represent Boolean functions and to manipulate them, but today they are also used in synthesis and also for formal verification. There are software packages which are already available in the public domain, using which you can do or carry out a number of different kinds of manipulations, reduction on BDD. So, any BDD based implementation, whatever you are implementing, you can use those packages to start with, those are already there. So, you can simply use them and you can build up your system. So, in our next class, we will be starting to talk about synthesizing starting from a slightly higher level. We will be talking about high level synthesis. Say, starting from a behavioral description in a language like Verilog. So, how do you go about doing it? What are the different steps of transformations? So, how do you ultimately land up into a hardware implementation, typically at the RTL level, register transfer level? Okay, that we will see next time.